Hi everyone, I welcome you all to this 11th lecture, and that will be going to be the last lecture of mechanical properties of fluids. So far we have discussed about the fluid statics, fluid dynamics, then fluid dynamics of ideal fluids, and then we have discussed about the viscosity, and then we have uh, we are currently on the concepts of the surface tension and related applications. So let me start today's lecture with by finding excess property, excess pressure inside a bubble using a energy conservation method. Okay, excess pressure inside a bubble using energy conservation. So basically, when we have this bubble, so this is a air bubble, sorry, air drop. Bubble is of soft, so that's the difference. So it's a drop. So there is a difference between drop and bubble. Keep this in mind. So drop is of liquid without just pure liquid, and bubble is of soap because, and we call it as bubble because inside bubble there is a air and there is a thin film. So this thickness of bubble is there are two films. So bubble is basically like looks like this in 2D if you see. So this is a bubble because it has two surfaces. So that is bubble, and inside there is a air, and it's a normal drop or drop of liquid. So, so we are here, we need to find out the excess pressure inside this. So consider that, so to find out the excess pressure inside this and why there is a excess pressure, that's the question. So if there is a pressure outside that is P naught and there is a pressure. So what happen is there is a surface tension that is acting on the surface due to the curvature. So these surface tension try to pull this liquid. So these molecules, these are having water molecules are having their cohesive force because surface tension is the tension is directly proportional to cohesive force. Cohesive force means interaction between between like molecules. So there is uh, extra pressure so that it will remain in. So there should be some extra pressure to maintain this spherical shape. Okay. So so let's say this is PL. So consider that you are expanding this bubble. So this is at t is equals to 0. At some times you are expanding this bubble. So let's say you expanded this bubble to delta r radius. So that is delta r. Initial radius is r. So the work done in expansion is surface area. Sorry, surface tension. So that is energy per unit area into change in area. That is ds. So that is S into final area is 4 pi r plus delta r square minus 4 pi r square. So that will come out to be 8 pi r delta r. I also told you that you can also calculate this ds. So we need to find out this ds with dr. So S is nothing but 4 pi r square. So ds by dr is 8 pi r. So ds in terms of radius is 8 pi r delta r. You can write delta s to be 8 pi r delta r. And this work done of expansion should be balanced by the, so this work done of expansion has to be balanced by this pressure change. So that comes out to be force into displacement. And this force is due to the change in pressure. So that is work done in expansion is balanced by the force force into displacement. So that forces because of this pressure difference, that is PL minus P naught, and displacement is 4 pi r, that is 4 pi r into delta r. Okay, so this we can equate these two things, and as into 8 pi r delta r is equals to PL minus P naught 4 pi r delta r. So r delta r will go, 4 pi will go to, so PL minus P naught is 2s by r. So basically this is the excess pressure that is maintaining the shape of bubble. So let's look at one question. So shape of drop. Sorry for this. If it is a bubble, then we have two surfaces. So then PL minus P naught comes out to be 4s by r. Okay. Now let's look at one question. So the question is, we have a air chamber and there are two bubbles. Keep in mind, now I am saying there are two bubbles. So one is of radius 2 centimeter, R1 is 2 centimeter, and another one is of radius 4 centimeter. 4 centimeter. This is air chamber. Surface tension is given as 0.04 Newton per meter. So that's the surface tension of this soap with air. So we need to find NV by Na. NV are the number of molecules, and where NV is the number of molecules inside a soap bubble, because inside a bubble there is air, as I already told you. So this air has some number of molecules and we need to find that number of molecules inside that. So the options are NB and Na, both are options are 2, 3, 6, 4. Try this question. We need to think about whether it's a number of molecules. So now it's a chemistry concept. Okay. So if we need to relate number of molecules, so with the volume, so we have and that too of gas. So we have a ideal gas law. So you have to think about it yourself, as it is not given in question. So NB by Na. So first I should relate using ideal gas law, number of molecules with the volume. So we know that PV is equals to nRT, N is nothing but PV by RT, and we need to find NB by Na. So that is PBVB, because this system is at same temperature, because the same air is there for the both, and this is the only single chamber, so there shouldn't be any temperature difference for at least these two bubbles. So PBVB, so RT is same for both. So PV, so the ratio is PBVB divided by PA, and PB is the excess pressure. So PB is the pressure inside the pressure inside a soap bubble. So PB and PA are the pressure inside the soap bubble. Okay. So we know that Pi minus P out is equals to 4S by R. Keep this in mind. Why this is 4? Because it's a bubble. Don't do this mistake. So this is the mistake that is frequently done by many people, and you will get negative marks because of this small mistake. So Pi is P naught plus 4S by R. So NB by NA is VB by VA into P naught plus 4S A by RA divided by P naught plus 4SB. Sorry, this this is B and V is O. So that is B SA by RA. Okay. So VB, we know that is 4 upon 3 pi R cube. So 4 upon 3 pi will cancel out with each other. So RB cube divided by RA cube. P naught. So P air is, that is given. So that is 8 Newton per meter square. So P air is 8 plus 4 into surface tension, that is 0.04 divided by RB. So RB is nothing but 4 centimeters. So that is 0.04. Now P naught is again 8 plus 4 as it is. Surface tension of A is 0.02 divided by, so surface tension is same, but the radius is different, 0.02. And RB is 0.04 cube divided by 0.02 cube into, so this will 12 divided by 16, 64 divided by 8 into 12 divided by 16, 16 2 is 62, 2 2 6 12. So answer is 6. Okay. Now let's move on to the last concept, that is related to the surface tension, that is capillary action. So I told you while telling about the surface tension that uh, the wick of cotton uh, gets wet and there is some rise of water if you dip it into the some water bath. So we can define capillary action as, so we can define capillary action as a phenomenon where ascension of liquid or the rise of liquid through a tube takes place. This occurs due to the adhesive and capillary forces. Narrower the tube, higher will the liquid rise. So we'll derive this, why this is so. So we have a water, let's say water, and we have this meniscus that is dipped inside that. And what happens that the water rise into this meniscus and formed a meniscus. So water rises and formed a meniscus at some contact angle theta. So this contact angle is here in this case is defined as the contact angle for capillary rise is the angle between the tangent to the liquid surface, to the liquid, and tangent to the solid that gets wet. So that's a theta. So this is theta. Okay. So why this is rising? And so first we will be deriving this formula that relates the surface tension with this contact angle, and we also call this as a Jurin's law also. That relates contact angle with surface tension. So consider that there is a rise. So this is the surface, and there is a rise in height of this meniscus, that is h. So we have just look at this. We have what we have found out is, so pressure inside the liquid droplet is greater than pressure outside. So if there's a meniscus, so this is actually a part of some circle. Okay. So if I zoom it out, so it will come out like this. Okay. And the meniscus is just this. The meniscus is just this. So if this is the radius r, and this is the radius of the tube. The tube is like this. The tube is like this. So small r, consider small r as the radius of tube, and this is the radius of the meniscus, that is capital R, and this angle is theta. This angle is theta. I will put it. So what I'm saying is, so this meniscus is this. So small r is the radius of this tube, this capillary tube, and this is the contact angle, that is theta. So can we relate r with r? So we can easily relate this like this is theta. This is, if this is theta, this is tangent to it. This is 90 degree, and we need to find out this. This is also 90 degree. I can zoom it out. This is the radius of meniscus. Now, this is the meniscus. So this is meniscus. So this color is actually showing the meniscus. So this color is actually showing a meniscus, and this angle is theta. This is radius of this tube, and this is the radius of this meniscus, that is capital R. Okay. So this is theta. This angle is 90 degree. So this is also theta, because this angle is 90 minus theta, then this again is 90, then this again is theta. I think you get it done with this. So you can relate this capital R with a small r. So cos theta is r cos theta is small r. So cos theta is nothing but r by capital R. So this is the first thing. So now what we need to find out is, let's find out the pressure at this point. So pressure here is P naught plus pressure. There is some pressure, so because of this meniscus is like this, so that is some extra pressure due to this surface tension, and because this meniscus is like this, so that is P naught minus 2s by r. So pressure here is higher, so that is negative, plus rho gh. So that is pressure at this point x. And if you find out pressure at this point, that is nothing but P naught. So let's call this point as y. So Py is P naught, and we know Px is Py. So that comes out to be P naught is equals to P naught minus 2s by R plus rho g h. So from here, R is the radius of meniscus. Keep this in mind. This R is the radius of this meniscus. So that is a, because this is a part of a this meniscus is a part of this sphere and this radius is R. So that R is capital R. So what we get is H is 2s by R rho g, and in terms of the tube radius, so that comes out to be 2s by R rho g cos theta. Okay, so H is 2s by R rho g cos theta, and there will be a rise only when theta is less than 90 degree, and theta is less than 90 degree, then only this H comes out to be positive, and that is the rise. Then liquid rises. If theta is greater than, and that's the spontaneous process. If theta is greater than 90 degree, then liquid will not rise. So I want to point out one thing, that there is this rise is because of the cohesive of the competition of the cohesive and adhesive forces. So cohesive and adhesive forces. So cohesive forces means molecular attraction in the molecules, between the molecules of same kind, and that is molecular attraction, molecular attraction between two different species. So the liquid will rise only when adhesive. The liquid will rise only when there is a contact angle that is less than 90 degree and the surface tension is lesser, which means to say that cohesive forces are lesser compared to the adhesive forces. So because adhesive forces making it to make it to rise at some particular height. Okay. So that is the concept of this. And I want to tell you one thing, that this contact angle is different when you have a drop of a liquid over a free surface. So don't get confused, because here the way we calculate the contact angle, let's say here in the capillary that is also water, in this that is also water. So the contact angle here is theta. So here, if theta is less than 90 degree, then we can say that this surface is lyophilic or solvent loving, or we can also say that hydrophilic for the case of solutions if there is a water molecules. So hydrophilic if theta is less than 90 degree. If theta is greater than 90 degree, that is for the case of mercury. So the contact angle is greater than 90 degree, around 135 degree. Then surface is hydrophobic. And so the surface is hydrophobic. So so that's the difference between this contact angle and this contact angle. Now let's take some questions. So I have around 15 minutes. Okay. So let's take some questions. So we have a capillary tube that is in a bath of water that is 5 centimeter. Surface tension of water that is 0.075 Newton per meter. Radius of tube is 0.5 mm, theta is 0 degree. Then find the difference in pressure. Find the difference in pressure between the point between a point that is 5 centimeter below the surface of capillary and the atmospheric pressure. So we need to find out the difference in pressure between the pressure at this minus atmospheric pressure, that is P naught. So let's consider this point at X. So we need to find delta P, that is Px minus P naught. Sorry, P naught minus Px. P naught minus Px. So we know Px is nothing but P naught minus 2s by R plus H rho G. So delta P is nothing but P naught minus P naught plus 2s by R plus H rho G. So it comes out to be 2s by R plus H rho G. R, capital R is small r cos theta. Theta is 0, so that is small r. That is 2 into surface tension given, that is 0.075 divided by R, that is 0.5 into 10 to the power minus 3 plus height is 5 centimeter, 5 into 10 to the power minus 2 into density is, so that is the density of fluid, so that is 10 to the power 3 into 10. So this 1000 will cancel with this will become this, so 544 4 into 75 plus 500, so that comes out to be 800 Newton per meter square. Okay. Now let's look up one previous year JEE question. The question is, so we have given a capillary of different shape. Capillary of this shape we are given. This angle is alpha. There is a liquid rise inside the capillary, and that is, the capillary is something till here. So that is H. This is given as B. B is this radius of the surface. So we need to find out the excess pressure. Options are 2s by B rho G. So this is B. This is B into cos theta minus alpha. 2s by B rho G into cos theta minus alpha by 2. 2s by B rho G cos theta plus alpha. 2s by B rho G cos theta plus alpha by 2. Okay, so try to solve this question. It's a bit tricky question, that's it. Some geometry type. Okay, so let's zoom out this meniscus. So it is something looks like this. Okay. So consider this end to be very near, such that if this is alpha, so this is alpha by 2. This angle is theta. And this is we know that any meniscus is a part of some circle. So that is related to it like this. So that is R. So always what is the excess pressure is? So we know H is 2S by rho G R. 2S by R rho G. Okay. So we need to find R in terms of B. So this is B, this is theta, this is alpha by 2. So if you do this line and this line, and we are extending this cone in this direction, so that is alpha by 2, this is theta. So this angle is, this is tangent to this, so that is 90 minus alpha by 2 plus theta. So that is 90 minus alpha by 2 plus theta. Again, this angle is 90 degrees, so this angle comes out to be alpha by 2 plus theta. So cos, so R B is equals to R cos alpha by 2 plus theta. So R comes out to be B by cos alpha by 2 plus theta. So H comes out to be 2s. So here we need to find H. So 2s by rho GB divided by cos alpha by 2 plus theta. So the correct option is this. I have some more time. So let's consider a tube of insufficient length. Like to say, let's say H is for any liquid, the formula is H is 2s cos theta by R rho G. Basically, HR is 2s cos theta by rho G. So for a given liquid, the height, that is H, the rise. So I can call it here is rise. H rise is less than, is greater. So height of rise is greater than the height of tube. So if you have given a tube such that the liquid rise, so the liquid rise till the top, what will happen? Whether it will fall outside that or not. So the first thing is that water will not come out of it. That's the first answer. So water will not come out of the meniscus. But then what will happen? Then what is that thing that is balancing it out? Then what is balancing the forces? So the forces are actually balanced by the curvature, or we can call it as the radius of curvature. Because for a given liquid, this, if you put R in terms of radius of curvature, then H rise into R is equals to 2s by rho G. The surface tension of a liquid is fixed, rho and G is fixed for a particular liquid. That means to say that H rise into R is constant. So if this height is not, so the height of tube is greater than this, then what will happen, that the radius of curvature manage this rise such that this will remain constant throughout. So the liquid will not go out. This will balancing out each other, and we have this term, this H rise into R to be constant such that H rise is inversely proportional to radius of curvature. That is the important thing. So we have time for one last question to discuss. The question is, and then that's the end of the mechanical properties of fluids. So we have a meniscus in which there is a rise. The height of tube is 4 centimeter, and this is 2 centimeter that is given. Now tube is tilted at 60 degree. Now the tube is tilted at 60 degree. So there is again some rise that rises. So we need to find out this length L. The liquid is same, everything is same. This theta is 60 degree. Are we allowed to check this, what this height is? So the question is, find L. So that's a simple question. So from the concept of fluid hydrostatics, that H is nothing but the same as like this, because pressure doesn't depend on the pressure will not going to depend on the shape of the meniscus. So H is same, that is 2 centimeter. That is for sure. So can we relate H with them? Now we know H. So sine theta, I guess, is H by L. So from here, L is H by sine 60. So L is 2 divided by sine 60. Okay. So that's the end of this discussion. Mechanical properties of fluids. From tomorrow onwards, we will be going to start the thermal properties of material. Okay. Thank you.